Okay, so here we're going to be talking about decay processes. So you're going to have some population, could be, in this case, probably atoms that are decaying. So we're going to have N naught, so our number of those atoms and the starting point that undergo some decay process at a rate R. And so we're going to have a probability. So probability that one of them, I'm trying to keep this general because it's kind of, math is going to apply to a variety of different physical systems. Probability that one of them decays going to be, well, we're going to just use P for probability, and we're going to say, well, it's going to be R times delta T. So, you know, the faster the rate of decay, then the more likely that it's going to decay, and the longer we wait, the more likely we're going to see decay. So our probability of this happening to a particular one in the population is going to be a combination of these two factors. But really what we're going to look at is, well, what's going on in terms of the entire population. So I'm going to say, well, the number of decays in the whole population in some time interval, so we'll say delta T. It's going to be, well, we're going to have, so N, so the number of decays, so the number of these decays is going to be the combination of N, how many we have in the population, times the probability that any one of those is going to decay at a given time. Now, really, this number of decays is telling us the change. The change in N. How many of these atoms, for example, have changed from one element to another, or the electrons fallen from some state to another, something like that. So our change is actually going to be N, and then for probability, I'm going to substitute in these two values, the rate and time passed. So our delta T. Okay. So now we've got two things that are changing, so I'm going to bring them over, and so we've got now an expression for the change in N over the change in time. And this is going to be equal to negative Rn. And I'm including this as a negative because we're going to have this rate is going to be a decay rate, so there's a negative sign there. And so really, we've got these deltas, but we can turn this into proper rate. So we're going to have some decay rate, and that's going to be our dN dt. So our formal rate here is going to be equal to negative Rn. Okay, so here we've got a nice expression for the decay rate. But what we really want here for practical purposes is some equation for, I'm going to say N at T, i.e. how many of the original population do we have at any given time. That's far more useful. So I'm going to close this part off. What we're going to do is we're going to take this expression and we're going to rewrite it as dN over N is equal to, and then we've got negative R dt. So all I've done is I brought the dt over here to this side, and I brought the N over with the dN on this side. So that way I've collected the N's here, and I've got the dt here. Now what I'm going to do here is I'm going to integrate both sides. So on this side, I'm going to integrate from kind of time is equal to 0, so like our original population, d naught, all up to n, which is the population at some given time. And over here, I'm going to integrate. Just here, kind of skipping a little step here, but really this is kind of t naught, so t at the very beginning, up to some point in time. But there's no t dependence for r, so that's why I left that outside the integral. Formally, I'd put the integral here and then pull it out. Okay, so then we can do this integral. So in this case, it's the integral of kind of 1 over n, and that's going to be ln n, and that's going to be evaluated at these two, so it'll be ln n minus ln n naught. That's going to be equal to negative RT, because t naught, it was going to be t minus t naught, but t naught's just 0. It's going to be our starting point. So I'll just kind of note here, t naught is just equal to 0 seconds. Okay. So now I can collect these two using my kind of properties of log functions. So this is going to be ln n over n naught. And then I've still got my negative RT here. And then I can take the exponential of both sides to get rid of this long term. And then we get n over n naught. So if I went e, put this all in the exponential, the e and the ln cancel. And then on this side I get e to the minus RT. Great. So I'm just going to do one more thing. I'm going to say n is equal to n naught e to the minus RT. Great. So now we have a very useful expression that's going to tell us how much we have of the original. It could be a decaying element. So we could have cobalt that's decaying or something. So how much is the original at a given point in time? Well, it depends on how much we started with. And then this term is telling us how much it's decaying. And it's going to decay in an exponential way that depends on the rate and how much time has passed. Now there's one more thing we can do here, and that is we're going to define another term we're going to bring in. So we're going to define tau. So tau is 1 over r, so it's the reciprocal of the rate. And this is also going to be called so this is the mean lifetime, for reasons we'll get into in a moment. Lifetime. Mean lifetime. Okay, so then we can rewrite this equation. N is equal to n naught times e to the negative t over tau. Okay. So now we've got this way of looking at it. And this tau term is really giving us a sense of the time scale of this decay process. So, for example, you could say, well, consider the n, so how many are in the population at a given point in time when, well, for example, t is equal to tau. Okay, well, when t is equal to tau, then n is going to be equal to n, but then t is tau, so these are 1, so it's e to the negative 1. So it would be e to the negative 1, and that's, so 1 over e n naught. Okay. Now, e, remember, so recall that e is equal to 2.71. We'll leave it at that. And so, 1 over e is equal to 0.71. 0.37, right? So at, t is equal to tau, n is 37% of n naught. Now we can keep going here and say, well, what about when t is equal to 2 tau? Well, then n is equal to, 1 over e squared naught. And then, t is equal to 3 tau. Well, then n is equal to 1 over e cubed n naught. And so, you're getting this exponential decrease. And so tau gives the time scale for how quickly the decay process occurs. So you've got a few key things here. We've got an equation now for the decay rate of some population, and we've got a nice equation for how many is left in the population at a given time. And we can write that in terms of the rate, or we can write that in terms of this mean lifetime. And we've kind of looked at this tau term a little bit to get a sense of, well, this is an exponential decrease here.